So today I'm going to be presenting the. Oh, can you see my screen?
Yep, you're
Yes.
seeing it.
Yeah. Okay. Okay. So today I'm going to present the presentation that I gave 3 weeks ago at Clay 2024. So this is the club's participation in all of the LifeCLEF tasks for LifeCLEF 2024. This was originally presented September 9th, and let's go ahead with this. So the outline for this presentation involves the team introduction, some of the individual solutions for all of the tasks for bird clay, geolife clay, plant clay, fungi clay, snake clay, and then I'll give a few thoughts and we'll have a little bit of time for questions if there are any. So as you all might know, we participated in the LifeCLEF 2024 conference, and we've been doing this for 3 years now. This year is our fourth year. So this started in 2022 with bird clay, and also in 2023. In both of those years, we won the working notes competitions. So, each one of those competition netted us $2,500. This last year, we had 31 members in spring, and we had 22 published authors over 11 working notes. This is across a mix of online and on-campus undergraduate and master students. These 11 teams were spread across 7 labs and 14 tasks. We had a couple of students who did this for course credit. So there's me, there's Murillo, Ritesh had like a CS 89 03 or 01. And we also had a few folks doing this for the deep learning course. So for the LifeCLEF lab, we had 12 authors with 9 graduate students and 3 undergraduates, and we had a submission for every single task. We had one for bird clay, we had one for plant clay, we had one for geolife clay, we had one for fungi clay, we had one for snake clay. And the thing that tied all these solutions together was that we really took advantage of models that have already some knowledge of a domain. And so we explored transfer learning techniques to take these existing models and to expand them into new domains or new data sets. We did a lot of exploration into low dimensional representations, low dimensional data-driven representations. So for example, on the lower left, you can see an embedding space of the top species in the BirdNet and bird clay data set. And you can see there's this clustering behavior, which is indicative of knowledge representation. And we also had a lot of shared infrastructure and tooling that made this group successful and limited the amount of toil that we did. So on the bottom right, you can see the pipelining that we did with Luigi and Spark and so forth. So just going into the solutions for bird clay, this is our third year running bird clay. And the big thing that we did this year was to basically use one model, the Google Bird vocalization classifier, to generate soft labels for all of our training audio. And so the goal for bird clay is to classify bird calls in soundscapes, to find where in the soundscape the bird exists and to figure out what species it is. We use the vocalization model as a surrogate model, and then we see whether or not we can learn some better performing models based on some existing models like BirdNet, which is a convolutional neural network. And we also try representation learning with Encodec, which is a neural audio codec. There's this pipeline, which we used. The biggest piece is this the transfer learning piece, and then the domain-specific multi-label classifier. So first, we take a look at the geometry of the various different model embedding spaces. So on the left, we have the vocalization classifier. You can see like tight clustering means that there is some sense of knowledge that's learned by the model. BirdNet also has pretty good clustering. And encodec kind of has this very scattered looking plot, which means that there may not be a whole ton there that's useful for bird calls. But yeah, we took these embeddings and then we built a very simple model on top of this in order to optimize for the multi-label task. So by multi-label, we mean that every 5-second interval that is in the test data set can have multiple birds in them. So we tried a bunch of different losses. We tried binary cross entropy, which is the standard multi-label loss. We tried ASL, which is this asymmetric loss that kind of builds on top of the focal loss. And we also tried sigmoid F1, which is a differentiable F1 score. We find that the BirdNet models using BCE actually performs really well. And so this is kind of an interesting result that by transferring the labels from the surrogate to this new domain specific one, we get some performance improvements. We also did a little bit of EDA. We got a new data set this year for unlabeled soundscapes, and we found that there's a very narrow band of species that actually exist in the test data set. And we tried utilizing these soundscapes in order to figure out whether we could learn something from this new unlabeled data. And we found out that we do learn something, but it's not all that useful. And so I think next year there's going to be more to utilize kind of the distributional shift in the unlabeled soundscapes that we're given. For LifeCLEF, this is predicting species distribution based on geospatial data. So we have a bunch of raster data and satellite data, and we want to be able to predict what plant species exists. And so down here, you can see all the different types of data types that we have in terms of rasters. We have this modeling pipeline that's based on building really simple models from, for example, just the latitude and longitude, or by building embeddings from the satellite imagery, as well as using low dimensional representations of the spatial data to make a very simple model of predictions. So one of the things that we do is we pre-compute all the tiles. So if you take a map of Europe, which is where this data set comes from, you can split it up into small grids, and then we can store these grids on disk so that we can basically run convolutional neural networks on them to learn some stuff. And so one of the things that we do is we can save a lot of disk space by applying the discrete cosine transform and taking the first 50 or so coefficients in order to compress the data. And this ended up being kind of an interesting technique. We also take those multi-label losses that you saw from BirdCLEF, BCE, ASL, Hill, sigmoid F1, and we apply it here, and we can see that there's a variety of results where ASL actually works pretty well, and so does BCE. But we find that our models really struggle to outperform basic baselines. And so there's a lot of work that needs to be done on LifeCLEF in order to kind of make it to the top of the leaderboard in some capacity. For PlantCLEF, PlantCLEF is identifying different plant species, and this year it changed because it became a multi-label image classification problem. So you're given this big plot of images, or an image that is a big plot, and you're trying to identify what plant species are in there. The basic technique here is to split the image up into grids, to embed that into a vision transformer that's been self-supervised on millions, billions of images, and then use these embeddings to build a very simple classifier that's able to rank by probability what species exists in the image. So you can see here on the left the vegetative plot, and on the right you can see kind of how we split this up into tiles. Using the embedding space of Dino, we can see that there is a very clear separation. So on the left, we have some DCT coefficients from the base Dino model. We have the classification embeddings, and then we see when Dino has been fine-tuned on the data set, it's even more precise. Yeah, we did this rank-based aggregate classification. So for every tile in the plot, We embed it, we figure out what's the most likely species, and then we just aggregate over all of these. And this ends up being a pretty efficient solution. We rank in the top 3 solutions for the task. Next, we have fungi clay. So fungi clay is identifying poisonous species of fungus. This uses a pretty similar architecture to the plant clay competition. We use Dino and whatnot, but it is just a multi-label classification problem, and we don't have to kind of deal with these larger images. So we tried some things with ResNet just to see how ResNet kind of represented the knowledge on these images. We tried Dino, and we got clear boundaries on the different species. We did a ablation study to figure out what pieces of information really help the model. So Dino, we get a base accuracy. If we add weighting based on the frequency of the classes in the training data set, we get some improvement, and if we include metadata, et cetera, et cetera. And we found that in the post competition, the Dino V2 ends up being kind of near the top of the leaderboard. And so Dino is actually a really effective technique for doing classification in this domain. Finally, we have snake clay. Snake clay is very similar to fungi clay. So we have a set of snake species that's representative of the test set in some ways, where some are poisonous, some are not, some they're easily confused, some of them are not. And we managed to make a solution, but there's a lot to improve here because we found out that there is a bug in the way that we indexed the classes. And so basically we got zeros for everything. But we had a lot of ideas that we played with during this competition. So for example, we played with segment anything. The idea here is that we get the snake from this image. It's really challenging to figure out which one's the snake. We tried OWLVIT, which is a multimodal model that has both text and images. And here we're asking, find me the bounding box of the snake. And so this is kind of an interesting idea. And the last is to use external snake data sets and to fine tune a CNN like YOLO. And so this might be a way to pre-process the data set for the competition. So yeah, those were all our solutions across all the tasks. One of the things is that one of the things that I thought made this year successful is that we really took advantage of transfer learning with these foundational models. And by doing that, it became a really cost-effective exploration. We could pre-compute embeddings for these data sets, for example, and then we could try differing the losses or differing the architecture of our final layer. And so this became a really effective and cost-effective way to play around with these data sets. And Dino V2 is really effective for images, so it'd be really interesting to see more models that encapsulate these domains. Is there a Dino for audio? Is there a Dino for geospatial data? I think it'd be really interesting to explore that more next year. Another thing is that I thought Clay is a really nice place, a safe place to try out techniques, even if they're like suboptimal. So this conference ends up being a really entry level and beginner friendly introduction to information retrieval, machine learning, and it's perfect for master students and really and undergraduates too. And the final thing is that I think one of the things for LifeCLEF is that we could have done a little bit better of cross-pollinating ideas, but you could see in all these tasks that there were elements of cross-pollination, and that really helped with being able to move faster, especially with having only a semester to go through these tasks. Yeah, so some thoughts on the group organization. Having teams of 3 to 5, having monthly milestone presentations, having weekly team meetings, and having these like 8-hour hack sessions over the semester it turned out to be a really effective way to get things over the finish line. And it really shows based on our participation in LifeCLEF and just our general showing in the in the working notes submissions. 11 papers is a big achievement. Um, some of the learnings from that is that uh, it's really useful to distribute accountability. So, we went from 5 people the first year, 5 people the second year, to 31 people this last year. And the way that we were able to scale up the team was to really distribute accountability from myself to a set of team leads. Um, and it was really challenging to finish all of the LifeCLE tasks. I don't think I would have been able to do it alone. So it really is a group effort in order to participate to the extent that we did. And I think the final thing that made it really successful is that there's a legitimate interest in the intersection between biodiversity and machine learning. A lot of the people who were on LifeCLE were, really, really interested in being able to use the techniques that they learned in class, that, the skills they may have learned at work, and to work on a task and a data set on a problem that can be really impactful. Trying to preserve birds, trying to prevent and save lives from mushrooms and snakes. I think a lot of these LifeCLE tasks are very applicable to real world situations, and so LifeCLE ends up being a really interesting lab. So I'd like to give a shout out to the LifeCLE organizers for putting together a very well-run lab, and to everyone who participated in our competition group. Yeah, thank you.
All right. Thank you very much, Anthony. Do you want to? I think we have 1 or 2 minutes for a couple of questions. So if somebody has a question, please go ahead, unmute yourself. All right.
I guess I can ask a question.
Yeah.
So yeah, Anthony and I, we've been working together for the past, I guess, 2 years. And I was just wondering, not only the main challenges of going from like one group to 12 groups was incredible, just that on itself was amazing to scale up. I'm wondering for the next year, what do you think is going to be our main challenge next? Since we already have a solid team with a lot of people, what do you think it's the next big thing?
Yeah, I think next year my aspirations is that we participate in every lab. So I think there's 14 or 15 labs. We participated in 7, but I think we could do all of them. The other thing is that I kind of want to keep growing our group. So going from 30 people to 50 people, going from 11 papers to maybe 15 to 20. And then I think it'd be really cool if we could get funding from the school. So I have a $10,000 funding proposal through GTSF. And if that's successful, we could have a really interesting next semester.
Yeah, that's awesome. Thanks.